Hello, class. So in this video, we're going to move on to section 2.3. In the previous videos, we finished section 2.2. Then we'll cover section 2.1, but a little bit later. I think it fits better with the topics we're going to be covering a little bit in the future. Okay, so section 2.3 is basically more examples of things you can model with differential equations. So I've done a couple before. Now, like the one of the velocity of a rock falling vertically, and then the population growth of bacteria colony, but it could be more generally any population with certain conditions. So because of that and because of time, I'm just going to cover one more example here in the lecture, and then in the homework, I'll ask you to do other examples of other things you can model. So again, this is not the only example you're going to see, it's just the one I'm going to be doing in the lecture. And you've seen a couple before already. So having said that, let's work this problem out. So suppose you have a mixing tank with 300 gallons of water mixed with salt. So this is usually called the brine solution. Meanwhile, another brine solution, so another mixture of salt and water, is being pumped into the tank at a rate of 3 gallons per minute. Now, this brine solution that's being pumped into the tank has a salt concentration of 2 pounds per gallon. Now, the solution is then stirred inside the tank, and then it exits the tank at a rate of 4 gallons per minute. So it's exiting the tank at a rate of 4 gallons per minute. Now that A of t denote the amount of salt in pounds in the tank at time t. Now, given this setup, if we further assume that no salt is created or destroyed inside the tank, meaning that all of the salt that comes from the mixture is either coming from the brine solution being pumped in or the salt that was already in the tank. Given that extra assumption, we can model this situation specifically. We can model the rate of change of the salt concentration using a differential equation. Okay. Now, a problem like this, it's easier to work with if you actually have a picture of what's going on. So I'm not the best artist, but I'm still going to draw you something that I think it's a good enough picture. So we have some brine solution, mixture of salt and water, that's being pumped in. Here I'm drawing it as just being, just falling into the tank, but it means the same thing. We have the tank here. Then we know that there's also brine solution that's exiting the tank. Now, just like you did in Calc 1, when you were doing problems like related rates or just word problems, you usually also want to label everything you can. The more accurate a picture you can do, the better the model is going to be. For example, here, I'm going to write what we know, that the rate in which this brine solution is coming into the tank is 3 gallons per minute. And then the concentration of salt in this brine solution that's going inside is 2 pounds per gallon. And I'm using LB for pound. Now, in terms of the solution, that's the rate of which the solution is coming out, we also have that information. We know that the salt is going, not the salt, but the brine solution is exiting the tank at a rate of 4 gallons per minute, right? So that's the thing that I had to fix a little bit. So this is exiting at a rate of 4 gallons per minute. And then we don't actually know yet the concentration at which it is exiting. So let me use the same color. So for the concentration of the solution that is exiting, we don't know what it is yet, right? It's not given to us. Now, this is basically the picture of what's going on. There's one more piece of information that we have that I'm gonna talk about in a moment. First, let's see what type of differential equation we need. Right? We're given that A of t, so it's obvious that the variable is t, the independent variable, so I'm just going to label it A. A denotes the amount of salt in the tank at the time t. Okay. So, given that, if we're trying to find what the rate of change of salt concentration or the rate of change of the salt concentration in the tank, how can we write that in terms of this variable? And I'm pausing you just to give you a moment to think. Want to write this differential equation that models the rate of change of salt in the tank. So actually, let me change it to just, because if A of t just denotes the amount of salt, then let's not worry about concentration here. Yeah, because if we do concentration, it's going to be just a little bit more complicated. So instead, let's just write a differential equation that models the rate of change of the salt in the tank, not necessarily the concentration of salt. So given that A of t, or A, is the variable that represents the amount of salt, and we're looking for the rate of change of that variable, then our differential equation should look like, let me use a different color, should look like dA dt, because we're trying to model the rate of change of the salt, and that's going to equal something. That's something we don't know what it is yet. We're going to have to figure it out. And we're also given another piece of information. Suppose that a mixing tank contains 300 gallons of water mixed with salt. Now, that means that there's already some salt inside the tank. We don't know what that amount is, but we know that there's something. So let's write that the amount of salt at time 0 is just some constant k. We don't know what it is, but we know there's some salt already in the tank. If we knew it was like 7 pounds, then we would just write 7 for k. But for now, this is what we have. We have a differential equation, which we still have to figure out what the right-hand sign is, and we have this initial condition. So it's basically an initial value problem. So that's the setup, and I recommend whenever you're doing a word problem that you try to write everything out, just like we did. And again, a picture like I drew here of what's going on helps. Now, how does what can we use in order to find what the rate of change of salt in the tank is? Well, there's two pieces of information. We know that there's some amount of salt that's coming inside at a rate of 3 gallons per minute. And we know that there's some amount of salt that's also leaving the tank at this rate. So the brine solution contains salt. So if there's brine solution coming in, that means salt is coming in. If there's brine solution going out, that means salt is going out. So I'm going to rewrite this differential equation, or I'm going to write this just as rate in minus rate out. Where rate in is the rate at which salt is entering the tank. And then rate out, or R sub out, is the rate at which it is exiting. The salt is exiting. Now, the reason why this differential equation works is because, again, we're assuming that no salt is created or destroyed inside the tank. That means that the amount of salt completely depends on the initial condition, right? The amount of salt that was inside the tank before we started pouring in and pouring out the brine solution, and the new salt that is coming in based on the brine solution, and the new salt that is going out. Okay. Again, if there were salt created inside the tank, we would need more variables basically, or another thing in this expression. But again, since all of the salts depends on the amount coming in, the amount coming out, and the amount that was already there, this basically works. Now, how do we find this rate in and this rate out? Well, let's use the information that we have and a little bit of unit manipulation. For example, for the rate in, we know that this brine solution is coming in at a rate of 3 gallons per minute. We also know that there's a concentration of salt of 2 pounds per gallon. So I have brine solution coming in at 3 gallons per minute. We multiply by the concentration of salt in that brine solution. That would be the rate in. Why? Well, look at what happens with the units here. The gallons cancel the gallons. So really what we're left with is 6 pounds per minute. So this is telling us that there's salt coming in, just salt, not concentration anymore, just purely salt is coming into the tank at a rate of 6 pounds per minute. Now we can do a similar sort of calculation for the rate out. Okay. So similarly, we know that the brine solution is exiting at a rate of 4 gallons per minute. The only problem is that we're not given the concentration of salt in this brine solution that is coming out. Since this brine solution is inside the tank, it's the same as saying what's the concentration of salt in the brine solution. Now, we don't know what that is, but we know the units. We know that we should have something that looks like, let me use, I guess I'm going to use the same color. Something that looks like, I wanted to use black. So something that looks like some amount of pounds of salt, I don't know how much that is, per gallon of brine solution. Now, again, I mentioned that this salt here is the salt inside the tank because this brine solution that's exiting is coming out from inside the tank. So the concentration of salt or the amount of salt in this this brine solution that's exiting is the same as the amount of salt in the mixture here in terms of concentration. We have a name for that. We know that A of T is the amount of salt inside the tank. So we can give this an actual name. Say that it's A pounds, okay? But based on how many gallons? So how many gallons of brine solution are in the tank at a given time T? Well, it's actually something that we can calculate. So we know that just in terms of the brine solution, you know that there's this solution coming in at a rate of 3 gallons per minute. And it's going out at a rate of 4 gallons per minute. So in terms of the amount of solution in the tank, every minute that passes, we're losing 1 gallon of brine solution. Again, because we're putting water or brine solution, at a rate of 3, removing it at a rate of 4. So we're gaining or we're losing 1 gallon of brine solution every minute. So we know we are losing, and if T is, so we usually use the variable T, right, for minutes. And again, we're working with the variable T here. So we're losing 1 gallon per minute, or if T is in minutes, we're losing T gallons per minute. Because again, T represents the amount of minutes, right? So how many minutes we have, that's how many gallons we're losing, right? So T gallons per minute. Now, this is not, I can't just put T here because T is not the amount of water or of brine solution in the tank. Okay, so how do I know what's the amount of brine solution in the tank? Well, we know that we started with 300 gallons of water or of brine solution, and each minute we're losing T. So we started with 300 gallons, and then every minute we're losing 1 gallon. So how much brine solution is in the tank at time T? Well, there's precisely 300 minus T gallons of brine solution. Again, because we start with 300, every minute we lose 1 gallon of brine solution. So we have T minutes, we've lost T gallons of brine solution. So we have 8 pounds of salt and a total brine solution of 300 minus T gallons at time T. So if we simplify this like we did above, we get 4A pounds per gallon. Again, oops, per minute. Again, the gallons cancel. We have gallons here, cancels with gallons here. Putting everything in, the rate of change of salt then is given by the rate in 6 pounds. And I'm gonna get rid of the units right now, just because I wanna write it just as a mathematical expression. But in practice, I think it's important that we know what the units are. So for example, I'm telling you that the amount that the amount of brine solution is given in gallons, that the salt is given in pounds, that time is in minutes. Just like in the bacteria example, the bacteria colony, I gave you that the amount of, that the days was, or the time was given in days. Just like in the rock falling, in free fall, I gave you that the distance is in meters and that the time is in seconds. So the units are important, but as long as you know what the units are, it's fine if you just, in terms of solving the differential equation, it's fine if you just write the numbers. You don't actually have to write the units. So we have 6 pounds per gallon, pounds per minute, that's the rate in, minus the rate out, which is 4A, pounds per minute. So this is our differential equation. Oh, and I forgot the denominator, sorry. 300 minus T. So that is our differential equation. Now, can we solve it? Or actually, before I ask if we can solve it, let me ask, is this linear? Is it? Well, let's check. There's a derivative here. Whatever's in front should have no dependent variables. Okay. There's only a constant 1. That works. Look at the other derivative. Again, think of A as the 0th derivative. Whatever's in front of it should have no dependent variables, just constants or the independent variable. Well, that works because what's in front of it is 4 divided by 300 minus T. That's an expression that only involves constants and the independent variable. So that works. Look at whatever's left. It doesn't have derivatives, multiply by it. If that doesn't have the dependent variable, then it works. 6 is a constant, there's no dependent variable. This is linear. What's the order? Well, there's one derivative, so it implies that it's first order. Right, because the highest derivative is the first derivative. Can we solve it? Well, it's not separable. You can try if you want, or you can check that there is no way to write, there's no way for you to write, let me move this screen. So there is no way for you to write the expression 6 minus 4A divided by 300 minus T. There is no way to write this as an expression only involving A times an expression only involving T. You can try, but you won't be able to. So this is not separable. It's not a separable differential equation. The only differential equations that we really know how to solve are separable, which means that we still don't have the tools to actually find a solution for this. So a function A that tells you the amount of salt at a given time T. But again, we weren't really asked to do that. All we were asked to was to find a differential equation that models the concentration, the change in salt, right? Not salt concentration, just salt. So, and that's what we have, right? The rate of change of the salt with respect to time, and we found this rate in minus rate out. So I go over this example because in terms of the setup, it's one of the most complicated ones, but I hope that it makes sense. I mean, there are some assumptions that we took, like salt not being created or destroyed inside the tank. And again, because of that, we know that the rate of salt has to change as dependent only on the rate in and the rate out. So hopefully that works. There was also a little bit of unit manipulation, so some things you would learn from in chemistry. So I won't spend too much time on that, but this is basically how you can model something like this. It's like a classical model that you'll see in any differential equations course. Again, we'll see more models, we'll see more examples, you'll see them in the homework and as we go through the course.